Hi everyone, my name is Márton Waszlavik, and just a short, not this way, that way, just a short background of what I've been done and what I'm gonna talk about. So I've been head of engineering at ImpressTV, and previously I've been working for Gravity R&D for like 6 years. Both companies are providing large-scale recommendation engines. So actually, we could hear many times in the keynote speakers mention recommendations. I was happy about it because now I'm talking about it. Okay, so some facts about these two companies. I remember when, like 8 years ago, we put together our first server, which was a desktop PC and which was located in our office, so it was a real startup. Today we have almost 400 servers, which are located in like 10 data centers or even more. And I think what's really crazy in numbers is the amount of user activities we are handling on a single day. So I was even surprised when I was gathering the information from Gravity and Impress and faced this number. So it's actually 1 billion user actions per day what is incoming to these personalization and recommendation services, which is crazy. And that 1 billion is not the data we deal with, that's the daily growth of the data we deal with. So it's been 8 years since we had one server, and now we have many, and now we have to face and handle this type of load. So my talk will be, just cherry picking a few stories during this big expansion we had. So naturally, I felt like if someone started talking about big data, then there is everyone feels it necessary to define what's big data really, because I think we kind of have no clear picture and no clear agreement on what it is, and I want to refine it because that will tell some directions why I'm talking about what I'm talking about. Okay, so I didn't find any good definition of big data, so I wanted to create my own, and this is what I end up with. Big data is something or anything that matches exactly two of the following criteria: big and data, and that's it. In fact, I was thinking why there is no real proper, better definition for this. And I think it's partially because what we mean under big data is really changing. It was something slightly different like 4 years ago than it's now. So we used to talk about Hadoop, then something more than Hadoop, then stream processing, and quite recently I think most people realized it's maybe not just about the tools, but it's also about the architecture. Okay, so as mentioned, this is not a specific term. Anything you do with big data is big data. So it's already recursive, and there is already anything. So it doesn't matter if it stores, translates, or understands the term. I also, when I was talking about it, I came into the conclusion that the definition of big data is essentially like the definition of art. If it is big data, if enough people say it is big data. And I think it's just really, the same thing with art. So if I draw a blue rectangle with a white strip, is it art? Am I an artist or not? Probably not, but if I can convince enough people, then it will be art. And I'd like to remember you that this painting has been sold for $44 million in an auction. So it's an important question, right? Okay, so if you can still see the screen, what I'm trying to say, that what I'm going to focus on today is more about how we can use today's big data technologies to help and enable scalability of our existing applications or new applications, doesn't matter, and data-driven architectures and stream processing, and how it changed slightly the concepts we've been working for many years. Okay, so first thing first, that's the traditional three-tier architecture we used to work with. So that's a front end, a back end, and a database. What happens when we try to scale it? Because it happened to us. So there are some parts which just scale nicely, and we are happy about that. Typically application logic, stateless components, usually it's not an issue, you can add more servers and then you just scale your service throughput. Then there are other parts that doesn't scale so well. Typical examples are session store and then session management on the server side. Caches, you probably need distributed caches because you have many servers and you want to share the state. And that applies on the front end and back end tiers as well. And then we have relational databases. So I'm not going to talk too much about the first two because I think today we have some real major solutions for those, like Memcache, Redis, and Cassandra, and of course this list is not exclusive, but typically these are the solutions you can use, or any other key value store to handle this type of issue. And the relational databases, now that's a little bit more difficult, more complex. So, so we all know relational databases doesn't scale to infinity, and that's why we don't like them. But there are a few things that actually relational databases are quite good at. I picked a few, and I'm not going to talk too much about this, but I guess you know what I'm talking about. So there are standard things that has been solved in the past 20 or even more years, which are really useful. That's why they have been developed. And if you are using big data, you will probably miss some of these or maybe all of these. Right? So security management, the extensive tooling support, anything that's there for the data constraints and data integrity checks. Indexing, CQL, the query language of course, and even performance. And by that I mean that probably you can't beat a key value store on single lookups, but there are some type of queries, like when you join like 3 or 4 tables, where CQL performance is actually quite good, and it can be like under 100 milliseconds or so, which is a type of service key value databases are not able to provide, and if you go for Hadoop or something else, you will probably see more than a second response times. Right, so maybe we don't have to forget CQL forever, and also CQL servers typically can still provide you a few things like replication, sharding, partitioning. Which just have the scalability. Okay, so there are typical, cases though when you are not using CQL, and probably number one has been already mentioned, which is the high performance key value stores. They are just better at this particular job. Then data is unstructured or maybe semi-structured, for example logs and a couple of other things as well. And then when data processing logic in your app needs to stream way too many data from your database. So that's probably something that Hadoop has managed to solve by moving the application logic to the data, not the other way around. So in these scenarios, probably CQL is not the right thing to use. Right. So after all, this is an improved three-tier architecture, and that's quite similar what we've been using. So you have a cache service. We, for example, use Memcache and Cassandra in this layer to offload the front end and back end data access. Then we have a traditional database, which is in our case SQL database, and then we have logs. We use Kafka to collect all the logs in a centralized way, and we have an HDFS in the background, so we archive data from the core database and also data from the logs and store it in a HDFS. So maybe SQL is not good to keep long years of data, but you can keep the most recent data in your SQL database, what you need frequently, and you can still have and still store the massive amount of data, historical data in HDFS or something. Okay, so these were some use cases how to use big data. I think, and I feel it important to mention that how not to use big data. And I've been in meetups and I had this conversation, and I had similar conversations too. We were talking about how you're using Spark, etc. And when I asked the question, okay, so how big is your database right now? Then I got the answer, it's 8 gigabytes. And it just doesn't make sense. It would fit in my notebook's memory. So why people are doing this, I don't know. But I think my point is that probably you shouldn't use big data technology in small scale, because we are engineers, we like to use the hardest technologies available, but maybe it's not a good decision after all. If you're using these technologies when you don't need to, you will face big overheads on performance, just the way you develop things, etc., etc. And I don't think it pays off. Okay, so then typically the answer could be that it doesn't scale, and in some cases that could be correct, but I think what's even more possible than scaling your implementation immediately is to make your architecture, software architecture, scalable. And how you do that? In most cases, it's of course impossible to predict what we work in a 3 to 5 years time frame. And usually when you do something like when you start a new product or a new app and start using Spark, you make a decision which should be done years later. And why you can't predict what will work in the future? Your product is changing, the technology is changing. If you just think about that most big data technologies doesn't even have version 1.0, then you understand why. And also the business environment is changing, so it's kind of would be impossible to tell at the beginning what will work in a 5 years time frame. Okay, so how to scale your architecture? Some ideas and some experience. Try to keep your application logic separated from your data access. If you do it well, then you could, for example, replace your database engine without your front-end developers, or even back-end developers would realize that. Loosely couple components so you can always keep flexibility and replace the pieces you really need. And also make the data flow easy and configurable between these components. Why to do that? Because then you can scale, upgrade, replace the right components you really need to without affecting the others. And microservices is just a good example. I think microservices is a great example of a scalable architecture. It does a little bit more than that, but if you think about its core concepts, then I believe that's something that scales really well. Okay, so probably another example on logs, but without, or before we move on, I'd like to ask a weird question. I don't know how many of you will understand this joke. I hope at least some. Okay, I got one, thanks. Okay, so typical, all rappers and hip-hop musicians, Ice Cube is on the bottom. So typically, a iconic rapper doesn't live too long, but Ice Cube somehow managed to not get shot until his 30s, so he lived longer. and eventually he became an actor, and eventually he became an actor in family movies. Right, so how it comes to logs, I had somehow a similar feeling when I put together my thoughts. So your application either dies after a few releases, or it lives long enough to use its logs as data sources for other systems. And this is how it happened to us. So we had, of course, logging in our application at the beginning, and of course we started to put more and more detailed logging into that application because it helps us to debug and troubleshoot when we have some issues in production. Then there are too many logs, so we started to write scripts to make our life easier to find bugs and issues. Then we even developed some tools that could replace those scripts. And after a while, we started to put some structured data into these logs because we just wanted to have more information and more valuable information. So we serialized like objects and lists and etc. into these log files. Eventually, all of these logs were collected in a Kafka cluster, and then we just started to use it because it became a good data source and probably a replaceable or unreplaceable data source for many things. So we could analyze the data we had in the logs and we captured in the logs for analytics, reports, maybe even monitoring. Okay. And as a last step, so we ended up documenting our own log format as one of our customers wanted to use that same Kafka data source and put the data into the data warehouse. So this is how we felt at the end. I think, so we did something and we just always improved it with a small step, and we ended up doing something completely wrong. At least this is my feeling about that. So how could this be done in the right way? So I think the best, well, you can have many approaches, of course, but I think the best if you just accept the fact that your logs are actually data, and you should thread it like data. So for example, you should use JSON format rather than plain text. Then you can still use a tool or an easy script that can print it human-friendly way, so you can still experience the same thing when you're looking at that. And I think this is a Node.js framework, which is a great example of how to do that. So this is a sample log line. And so you have everything in JSON. You even have some basic information here, like the host name, etc. So it's easy to collect it in one way, like in a centralized way, like Kafka, and you still know what's the source of the logs. And you have a nice CLI application just to make it more human-friendly to read if you want to, or even you can filter those. So I think so far it worked pretty well, and we were happy about that, so I can only recommend you to consider. Right. Next kind of story is around ETL and data-driven architectures. So I tried to simplify a small specification what came from us, what we did in the past. So let's just pick this example. So we have to implement an API to capture TV usage events. So it does mean that a lot of devices will send some usage events and usage statistics and metrics into our API. We need only a few of them. So for example, we need channel zapping. We don't need a volume control event, so we can drop those. Then we need to implement some data cleaning, of course. For example, we don't know too short events, TV watching events, because it doesn't matter. Then we need to do some data transformation, of course, and finally put it into a database. So this is the typical solution I bet most of you would end up doing for the specification. So you pick your favorite programming language, Java, C# or JavaScript, whatever, and you implement that interface, that API, and then eventually you do all the transformation logic, you code it, and then you write it to a SQL database. So, okay, and that would work. But here are some problems. So, specification, in most of the cases, there are always a phase 2, or there are always new ideas from the customers or from the product team, doesn't matter. So the specification will grow, right? And you will end up, or we ended up, pulling even more systems, or pulling data from even more systems then we had to, process even more data, and then we had to feed even more outputs, not just SQL. And last but not least, the whole debugging and troubleshooting of this very simple approach was difficult, because we have an API that works in production, we have no access to production. So we as developers, how could we work with that, or what can we do if customer says that it's not working, right? We have the log files, but if we don't find the relevant information in log files to troubleshoot the issue, how can we reproduce it? It's very difficult. So, so this is an improved solution. And what it does, it decouples the interface communication, the data flow, and the business logic. So, if you check out this one, it does the same thing. There's a really thin API layer that captures the data from whatever source and puts it into a Kafka message queue, whatever. We use Kafka in most of the time, or even simplifies. Then you have a business logic, which works in a very simple output, and it's independent from the real environment. And then you can put it to another message queue or Kafka topic, and eventually write it to SQL. What it does, so if you have more inputs and more sources, then you just have to write a thin application and put the same, or put the new data to the same Kafka queues. And equally, if you want these data to be processed in a Spark cluster or a Flink, then you have that Kafka topic, and you just have to connect to that topic, and you access this information fairly quickly. And what's the best is, if customer has some complaints, we can easily get some sample from the Kafka queue or from the files. So it's not a problem anymore that we have to call 5 different APIs at the same time to reproduce an issue. Okay, yeah, that's a quick summary of what I just said. And there is some even further extension that, just imagine that we also store in our little service that which customer is subscribed to which TV package. There is basic, family, and extra. So service will be called each time when customer changes the subscription. It was, for example, basic and now it's family, or the other way around. So how would we, again, approach this? So I think there is a straightforward answer we just seen before, but also it's a trap, and I'm going to show you why. So this is probably a simplistic approach to solve that problem. But then here is a question, but what you can probably expect. That please can you give me or provide me a report showing how many customers canceled their subscription in the past 30 days? And the answer will be no, because you just store the actual state in the database. And you can't really answer this question. You don't have the historic data, you just have a snapshot of your database. So if you, again, check out the other proposed solution, then you have a Kafka topic and a data stream and an event stream that will enable you to do some, just to reply that question, because you have the data. So I think in data-driven architecture, it's a really good practice to keep the data event stream as it is, and your database is actually nothing more than a snapshot of that event streams. So it's always calculated from that event streams. And of course, it decouples the interfacing from the business logic. Right. So just in a quick summary, I collected the takeaway messages. Number one is your logs are data. Number two is that keep your architecture scalable and not implementation. Then loosely couple components. And finally, and probably that's the most important one, what you should remember, is data-driven architecture. So try to change the way how you think on typical problems and typical solutions, and try to focus on the data itself and the data event flow, and solve the problem to how to transform that data flow into the right source for your items. Right? That's it. Thanks for listening. And I guess if you have questions, time is over, so you can find me after this. I have 5 minutes for questions. Great. There's a question.
Thank you. When you were speaking about logging, and there was a logging case, you have mentioned Elastic Stack for logs, like Elastic, Logstash, Kibana.
Yep.
You didn't want to go into details, or you don't like this implementation of the solution? Thank you.
Yeah, I think that's a right use case, and probably it's pretty much the same thing I was saying. So if it's already in JSON format, your data that you later want to filter or analyze or create statistics, if you store it in a structured format, your life will be much easier because you just need to use that Kafka topic in the Elasticsearch adapter, and you're done. Your job is done. You just need to create the right filters and right search criteria. If you have plain text logs, then your life will be much harder because you need to serialize and deserialize that format.
But you have Logstash, which has a lot of plugins.
Yeah,
you can
yeah.
say that, so you can store JSON, plain text, and when if plain text is structured,
yeah,
you can use it.
Yeah, of course, and we use it. I'm just saying it's probably a more painful way to write it in plain text, and then later we probably had more than 10 different tools, scripts, and applications where we have to parse our own log format for no reason, because we could just use something like JSON, and then our semi-structured data is already in a semi-structured format.
Makes sense. Thank you.
Any other questions? Thank you.
Thank you.